Okay. So, this is the problem solving session. Here we will take up the problems based on the lectures in the last week, that is from 6th lecture to 10 lectures. So, tutorial 2. Okay. So, let us see the first example. Suppose prove that if x and y are two distinct points, y are two distinct points in a metric space, x t, then there exist two disjoint open set U and V such that x belongs to U and y belongs to V. Now, x and y are the two distinct points in a metric space x t. So, distance between x and y is positive. Let us choose epsilon to be half of this distance and draw the ball centered at x with the radius epsilon and another ball centered at y with the radius epsilon. So, these two balls are disjoints and in such that x belongs to the one ball u and y belongs to this. So, basically u is the set of those point y whose distance from x y is less than epsilon, v is the set of those point such that whose distance from this is less than epsilon and epsilon is less than half of distance, therefore, these will be disjoint and prove satisfied. So, nothing to prove much. Now, next example is prove that the set S, which is the collection of ordered pair x y belongs to R 2 such that 3 x plus 5 y is less than or equal to 2 is a convex set in R 2. Okay. So, what is the convex set? The convex set we mean. So, let us first define the convex set. Convex set we say a subset A of a vector space X is said to be convex. The convex set in X if for all x by in A, the set of element z where the z is T x plus 1 minus T y. This set where the T is lying between 0 and 1 contained in A. It means a set A is said to be convex in a metric space x t if we picked up any 2 point x and y, then line segment joining with this must be lying totally inside it. So, here we have to justify that this set is a convex. So, let us take the 2 point, let A is a point x 1 y 1, B is a point x 2 y 2, both are the points belonging to S, okay, belonging to the set S. Then since A and B belongs to S, therefore, they satisfy this condition 3 x 1 5 y 1 is less than 2, less than or equal to 2 and 3 x 2 5 by 2 is less than or equal to 2. Now, we want this set to be convex. So, consider the lambda times of A plus 1 minus lambda times of B. If I substitute this thing, then this basically becomes lambda times 3 x 1 5 x by 1 plus 1 minus lambda times 3 x 2 plus 5 by 2, just manipulating, and this is less than or equal to 2. So, we basically we are getting less than equal to 2. Therefore, this point belongs to this. Therefore, this lambda A plus 1 minus lambda B is in S. So, S is convex. This calculation please verify, because this is simple and thus we can go for it. Okay. Then next example is whether the set X belongs to R such that X is not equal to the set of integer. X is integer, set of integers. Okay. X is not an integer, we are just denote the set of integers, all integers. The set S is open, prove it. So, this is our real line. These are the integers 0, 1, 2, 3, minus 1, minus 2 and so on. So, we are taking the set as those real numbers which are not integer. It means, we are basically dropping these things. So, we are getting this interval 0 1, then 1 2, then similarly 2 3 and so on. So, these are all open intervals, and union of these open intervals, say u 1, u 2, u 3 and so on. Similarly, here also. So, these are all open, and countable union of these open set, countable union of these open intervals is the set S, and since each one is open, therefore, S is open. Countable union of the open set is open, therefore, this set is open. So, the set is an open set. Okay. Similarly, prove that the set X belongs to R such that sin X is not equal to 0 is an open set, in R. Okay. The solution is, let us consider the set S which is such that sin X is 0. So, what should be the element of this? It will be the element n pi type, where n belongs to the integers, set of all integers, Z is the set of all integers. So, we are having this 0, pi, 2 pi, minus 2 pi and so on. Now, we claim that S has no limit point in R. Because the reason is, if I take any point, because take any point x belongs to S, then the neighborhood of this, neighborhood of x of say radius half cannot contain infinitely many points of this, contain infinitely many points of S, because its S point is only these points, that is all. So, if we draw any neighborhood, then the points which are available in this domain, this interval is not the point of S. So, basically no point of this is a limit point in R. Therefore, we can assume that all the limit point of S is contained inside it. Therefore, S is closed. Okay. So, since S is no limit point, so all the limit point we can assume this is a. Okay. So, once S is closed and the given set is the complement of this, so it is open. Complement of the closed set is open, therefore, this will be an open set. Okay. So, this now next example, let A be the set n cube plus minus 1 to the power n by n of this type, where n is the set of natural number. Then question is, find the supremum of this set A. Okay. Supremum, we know every least upper bound of a set. If a set is there, then one can find an upper bound. Among all the upper bound, if we take the lowest one, then least upper bound is called the supremum. So, if A is an supremum of a set A, then if I take it slightly more than that number A plus epsilon r, then all the elements of the sets are less than equal to that number, and if we take slightly lower than this, then after certain stage or the terms of the sets will be greater than equal to this. So, this is the definition we define the supremum of a set. Okay. So, we are interested in finding the supremum of this. Now, what is this number? For n belongs to capital N, we have n cube plus minus 1 to the power n divided by n, and that will be equal to what? N square plus minus 1 to the power n, which is greater than or equal to n square minus this, because a plus b more is greater than equal to a minus b when they are positive. Okay. So, this is, and since 1 by n is less than 1, therefore, this is further greater than or equal to n square minus 1. Now, the right hand side set B, which is n square minus 1, is an unbounded set, because as n increases, the number of points are keep on increasing. So, supremum of this set will not exist. Therefore, supremum of B A does not exist. So, is not the, it means it is not, does not exist. Okay. Next, now some example on the covers. Justify whether the family G n plus 2 over n plus 1 comma n plus 1 by n, where the n is natural number, forms an open cover for the set 1 2. Open cover we mean a collection of the open sets whose arbitrary union covers the set A, then it is called the open cover. Say for example, if I take the minus n and n, this open interval covers the entire real line, is it not? Or maybe minus 1 by n to 1 by n, union of this covers the 0 1 interval, okay, open interval 0 1. So, such a set is said to be an open cover of this. So, we are interested whether this family, that is this is a family of the open intervals n plus 2 over n plus 1, n plus 1 by n. So, basically the interval are when n is 1, it is 3 by 2 to n is 2 by 1, then n is 2. So, it is 4 by 3 and then 2 3 by 2, then n is 3, 5 by 4, then 3, 4 by 3 and so on. So, this is the interval, this is 2, here is 1. Now, 3 by 2 2. So, 3 by 2 2 will be this interval, okay. 3 by 2, 4 by 3 to 3 by 2, this is 3 by 2. So, again this is this interval and keep on doing. So, if I take the union of these intervals n plus 2 over n plus 1, n plus 1 by n is 1 to infinity, then this set does it cover the closed interval 1 2 or not. Obviously, it does not cover the closed interval 1 2, because the 1 we are not getting 1 when you are starting with this, we are not getting 1. So, 1 and 2 do not belongs to 1 and 2 do not belong to this union. Therefore, it is not the open cover. Cover of 1 2. Okay. So, this is not an open cover of 1 2. So, this one we have to justify it by this way. Okay. Next is okay. Prove that G, which is the collection of these open interval 1 by n comma 3 n, where the n belongs to capital N, is an open cover of the 0 infinity, and find subcover of G. So, it is very easy solution. When you take the 1 by n 3 n, each one is a open interval, and when we take the countable union of this, then obviously it covers 0 infinity. So, first part is it is an open cover of 0 infinity. Okay. Now, we are interested for the subcover. So, if I take the collection G dash as the set of all open interval like this, where n is integer, then also we say 1 by 3 n 6 n, when you take the union n equal to 1 to infinity, it also covers 0 infinity. So, this is also this G dash is also an open cover, G dash is also, but what is the difference here? When you are taking 1 3 n, then n is half, so half and 6 like this. So, basically this is n is 3. So, it is 1/3 9 and like this. So, this is 1, this is taken, this is third like this. So, first one is this one, and countable union of this give us the 0. Now, in the second one what we are doing? We are dropping among these intervals, we are choosing this in neighborhood. Similarly, others neighborhood by dropping many in between the other intervals. So, from the given set of the open interval, we are picking only the intervals and dropping some finite number of interval in between. Therefore, this is a subset of G dash. So, obviously, G dash is a subset of G, but G dash is also a cover, open cover. So, it is called the open subcover of G, that is all. Okay. So, this is what. Then next is prove that the set of all integers integer z is not a compact set. What is solution? the compact set we define in two ways. One is an Henry-Weyl theorem says a set is compact if and only if it is closed and bounded. The another way of defining the compact set is every infinite sequence, if it has a convergent subsequence, then the set is said to be a compact set. So, here we will use the second definition in order to justify the set of integer is not compact. It means, we are getting a subsequence of Z which is infinite subsequence of Z which is not convergent. So, since the n set of integer natural number is a subset of Z, and this sequence at n which is a subsequence of Z where n is 1, 2, 3 and it does not converge. So, 1, 2, 3 and so on does not converge. Therefore, a set is compact if any infinite sequence has a convergent sequence fails. So, this Z has a infinite sequence of set of natural number which does not converge. Therefore, Z is not compact. Okay. So, Z is not compact. Clear? So, this what we want. Okay. Let G be a collection of open intervals I n x belongs to R such that minus 2 n less than x less than 2 n belongs to natural number. So, that G is an open cover of Q. Q is the set of rational numbers. Okay. Solution is, so I n is basically set of all real numbers which lies between this x less than 2 n. So, basically we can write it x r such that mod of x is strictly less than 2 n, where the n is a set of natural number. Now, if we take any point x, let x belongs to Q. So, there exists a k, there exists a natural number k such that this x mod x is less than 2 k. We can always identify any rational number, one can identify the natural number such that the absolute value of k x is less than 2 k. It means, the x belongs to I k. Therefore, this belongs to the union of I n when n is 1 to infinity. So, every point of this, every point x of Q is covered by an open interval, which is open in open interval I n. Therefore, Q is Q has G as open cover, and that is okay. So, this is open cover for this. Okay. Then let us see few more examples on this. Convex sets, which of the following subsets of R 2 are convex? Solution. Okay. Sorry, these are the choices: x y such that mod x is less than equal to 5, mod y is less than equal to 10, B is set of all x y such that x square plus y square is 1, and third is x y such that y is greater than equal to x square, and D is x y such that y is less than equal to x square. Okay. So, let us see which of the following subsets of R 2 are convex. Convex, we know that take any 2 point of the set, if the line segment joining these 2 points lies totally in the set, then it is said to be convex. So, first part is the x y such that mod x is less than equal to 5 and mod y. So, if we draw the figure for this, mod x less than 5 means minus 5 to 5, and mod y is less than 10 minus 10 to 10. So, basically this one is the set. Now, this set obviously if we take any 2 arbitrary point x and y, the line joining this will always lie inside it. So, it is a convex set, nothing to prove for much. While the second set is basically the x square plus y square is 1. So, this is the only these points x square plus y square is equal to 1. So, if we take this 2 point A and B and line joining these 2 points, then this line does not belongs to the set, therefore, is not convex. While in case of C, if we look the x y such that y is equal to x square, then basically y equal to x square is a invert parabola, and this parabola is like this. Okay. X square is equal to y. So, y is greater than x square, y is greater than x square, it means the portion in this. Now, if we take any 2 point here, then the line segment joining these 2 points is always lies inside it. So, it is a convex set, while in the second case when it is less than x square, this is the portion. Now, if I take the point here and here, the line segment joining this does not belongs to this. So, this portion does not belong. Therefore, it is not a convex set. It is not a convex set. Okay. So, then now, okay, I think one more uncountable sets. Let us see. Last example for this is justify whether the set A x belongs to n such that mod x minus 7 is greater than mod x is finite, countable or uncountable. Solution is. So, let us draw the figure for this. So, x minus 7 will be this one. This is mod x minus 7, and this one is mod x. So, this is y. Now, we want the mod x minus 7 is greater than this. It means this point is 7 by 2, 7 by 2. So, if we write x to be less than 7 by 2, then obviously, if x is, then the mod of x minus 7 is strictly greater than mod of x. This is satisfied. Therefore, the set, but it is a set of integers. The x is justify whether this, when x is a set of natural number, it is a natural number. So, we have the point A as 1, 2 and 3. Therefore, the set is finite. That is all. Thank you.